Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 8, Projectivities in One-Dimensional Forms. Section 73, Characteristic Throw and Cross Ratio. Footnote, all the developments of this chapter are on the basis of assumptions A, E, P, and H0. Theorem 1. If M, N are double points of a projectivity on a line, and AA', BB' are any two pairs of homologous points, i.e. if NAB is projective with MNA', then MNAA' is projective with MNBB'. Proof that SS' be any two distinct points on a line through M, figure 85, and let the lines SA and S'A' meet in A', and SB and S'B' meet in B'. The points A', B', N are then collinear. Theorem 23, Chapter 4. If the line A', B', meets SS' in a point Q, we have MNAA' is perspective with center A', to MQSS' is perspective with center B', to MNBB'. This proves the theorem, which may also be stated as follows. The throws consisting of the pair of double points in a given order and any pair of homologous points are all equal. Definition. The throw T of MN, AA' consisting of the double points and a pair of homologous points of a projectivity is called the characteristic throw of the projectivity, and the cross ratio of this throw is called the characteristic cross ratio of the projectivity. Footnote. Since the double points enter symmetrically, the throws T of MN, AA' and T of MN, AA' may be used equally well for the characteristic throw. The corresponding cross ratios R of MN, AA' and R of MN, AA' are reciprocals of each other, chiefly Theorem 13, Corollary 3, Chapter 6. Corollary 1. A projectivity on a line with two given distinct double points is uniquely determined by its characteristic throw or cross ratio. Corollary 2. The characteristic cross ratio of any involution with double points is -1. This follows directly from Theorem 27, Corollary 1, Chapter 4, and Theorem 13, Corollary 2, Chapter 6. If M, N are non-homogeneous coordinates of the double points and is the characteristic cross ratio of a projectivity on a line, we have the quantity x' minus m divided by the quantity x' minus n, the quantity x minus m divided by the quantity x minus n is equal to k, for every pair of homologous points x. This is the analytic expression of the above theorem and leads at once to the following analytic expression for a projectivity on a line with two distinct double points M, N. Corollary 3. Any projectivity on a line with two distinct double points M, N may be represented by the equation the quantity x' minus m divided by the quantity x' minus n is equal to k times the quantity x minus m divided by the quantity x minus n, x' x being any pair of homologous points. For when cleared of fractions, this is a bilinear equation in x', which obviously has m, n as roots. Moreover, since any projectivity with two given distinct double points is uniquely determined by one additional pair of homologous elements, it follows that any projectivity of the kind described can be so represented in view of the fact that one such pair of homologous points will always determine the multiplier k. These considerations offer an analytic proof of Theorem 1 for the case when the double points M, N are distinct. It is to be noted, however, that the proof of Theorem 1 applies equally well when the points M, N coincide, and leads to the following theorem. Theorem 2. If in a parabolic projectivity with double point M, the points A', and B', are two pairs of homologous points, The parabolic projectivity with double point M, which puts A into B, also puts A prime into B prime. Corollary, the characteristic cross ratio of any parabolic projectivity is unity. The characteristic cross ratio, together with the double point, is therefore not sufficient to characterize a parabolic projectivity completely. Also, the analytic form for a projectivity with double points Mn, obtained above, breaks down when M is equal to N. We may, however, readily derive a characteristic property of parabolic projectivities from which will follow an analytic form for these projectivities. Theorem 3. If a parabolic projectivity with double point M transforms a point A into A prime and A prime into A double prime, the pair of points A double prime is harmonic with the pair A prime M, i.e. we have H of MA prime, comma, A double prime. Proof by Theorem 23, Chapter 4, Corollary, we have Q of MA prime, comma, MA double prime, A prime. Analytically, if the coordinates of MA prime, A double prime are MX, X prime, X double prime, respectively, we have, by Theorem 13, Corollary 4, Chapter 6, 2 divided by the quantity x prime minus m equal to 1 divided by the quantity x minus m plus 1 divided by the quantity x double prime minus m. This gives 1 divided by the quantity x prime minus m minus 1 divided by the quantity x minus m equal to 1 divided by the quantity x double prime minus m minus 1 divided by the quantity x prime minus m, which shows that if each member of this equation be placed equal to t, the relation, equations 1 divided by the quantity x prime minus m equal to 1 divided by the quantity x minus m plus t, is satisfied by every pair of homologous points of the sequence obtained by applying the projectivity successively to the points A prime, A double prime, ... It is, however, readily seen that this relation is satisfied by every pair of homologous points on the line. For relation 1, when cleared of fractions, clearly gives a bilinear form in x prime and x, and is therefore a projectivity, and this projectivity clearly has only the one double point M. It therefore represents a parabolic projectivity with the double point M, and must represent the projectivity in question, since the relation is satisfied by the coordinates of the pair of homologous points A prime, which are sufficient with the double point to determine the projectivity. We have then Corollary 1. Any parabolic projectivity with a double point M may be represented by the relation 1. Definition. The number t is called the characteristic constant of the projectivity 1. Corollary 2. Conversely, if a projectivity with a double point M transforms a point A into A prime and A prime into A double prime, such that we have H of MA prime, comma, A double prime, the projectivity is parabolic. Proof. The double point M and the two pairs of homologous points A prime, A double prime are sufficient to determine the projectivity uniquely, and there is a parabolic projectivity satisfying the given conditions.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.